Okay, so this is another way to solve for specific heat capacity. And in fact, we're going to do this in class as a lab. So we will get more practice with this on Monday. But I want to show you how it works and how the problems look. So many problems involve a hot piece of metal. So we take some sort of metal. We're going to heat ours in boiling water. And you're going to take it and transfer it into a cool calorimeter of water. So water that's just out of the sink. And a calorimeter is a device that we use to do reactions in it that are hot. You can buy very fancy calorimeters, but honestly, a styrofoam cup works just as well and is far more affordable. So our school calorimeters are actually just styrofoam cups, but they insulate the heat and they keep it in. Any calorimeter is going to lose heat to the environment, so it escapes out the top. That is always a source of error in a heat lab. The heat that's lost by the hot piece of metal equals the heat absorbed by the water. So we're going to take this hot piece of metal and we're going to put it into water. So here's our cup. We're going to, and it's filled with water, we're going to put our piece of metal in it, and the heat is going to transfer to the water until the metal and the water at the same temperature, because we'll have a thermometer in here reading the temperature. So we'll see the water be cool, and then we'll see it go up by a few degrees because the heat from that metal will make the water warmer. At the same, the metal will become cooler. Everything will end at the same temperature. We can measure the increase in temperature of the water and therefore measure the decrease in temperature of the metal. And we can use that to solve a problem. Problems like this look like above, and I would copy the problem into my notes so you see what it looks like when you're going back to study and look over things. So it says 150 gram sample of a metal at 75 degrees Celsius, okay, so a hot piece of metal, is added to 150 grams of water at 15 degrees Celsius. So that's our cool water. The temperature of the water rises to 18.3, and this is a key piece of information. This is the final temperature of the water. And it's always going to be reported that way, but you also need to know that this is the final temperature of the metal. It's going to be the same. They're going to have the same final temperature because we're waiting till they get to equilibrium. Calculate the specific heat capacity of the metal. We know that the heat gained by the water is equal to the heat lost by the metal. Therefore, Q of the water is equal to Q, this is heat, of the metal. So I can substitute in for Q mc delta T and mc delta T. I specified water and metal in my equation so that I'm certain to use the proper values in there. So now I can go ahead and start substituting some things in. Oops. The mass of the water was up here, was 150 grams. They happen to be the same in this problem, but very often they are not. So we have 150 grams of water. C is a constant, and I gave it to you earlier in this unit, and it would be provided for you, but you're going to get to know it. C for water is always a constant that we have access to, and it's 4.184 joules per gram degrees Celsius. Remember, that's how many joules it takes to raise 1 gram of water 1 degree Celsius. The change in temperature of my water, and I always like to keep my change in temperatures positive, and we'll explain when it doesn't need to be, but it just makes life easier, I think, is it went from 15 degrees to 18.3 degrees. So 18.3 degrees Celsius minus 15 degrees Celsius. The mass of the metal also happens to be 150 degrees, so I'm going to go ahead and put that in. 150 grams, grams. C is what I'm solving for. The specific heat capacity of the metal is what I'm solving for. Change in temperature is, my metal started at 75, but remember it ended at 18.3. That final temperature is always the same. But to keep my values positive, I'm going to do 75 degrees Celsius minus 18.3 degrees Celsius. So now I'm going to go ahead and go through and simplify. 150 grams times 4.184 joules per gram degrees Celsius. And then 18.3 minus 15 gives me 3.3 degrees Celsius is equal to 150 grams times C, that's still my constant that I'm looking for, and then times my new change in temperature here, which I'm actually going to subtract, is 56.7 degrees Celsius. I'm going to multiply anything that can be multiplied. So I'll do my 150 times my 4.184 times my 3.3, and I end up on this side with 2071.08. I'll worry about significant figures at the end. And I'll multiply my 150 times my 56.7 and get 8505C. Okay? Notice I've stopped worrying about significant figures and units. Since I'm solving for C, I'm going to go ahead and divide by 8505 and divide by 8505. So I'm going to take my 2071.08 divided by 8505, and I end up with C, because that cancels out, being equal to, and now I'm going to go up here, and 3 significant figures is sort of my limit. I do have 2 for that temperature. So I'm going to go with 3 significant figures, although 2 would be acceptable. 0.244, and since it's a C, my units are always joule per gram degrees Celsius. So when you do this on your test, how much work do you need to show? That's always the question that I get asked. Okay, I want to see you write the formula. I want to see you substitute it in. And I want to see the answer. If you choose to write out these 2 middle steps, that's fine. That's extra work, and typically students that do write that out do better. But I know many people like to just do it on their calculator. So when you're looking at what I'm grading for, I'm grading to see that you wrote the equation, that you substituted in everything correctly, and then that you provided me with the answer. To identify this type of specific problem, this is really looking at this one, it's a metal and it's added to water. It's sort of a unique, special, small subset of problems, and it uses this idea. So even though it's MC delta T, we're going to use this heat gained equals heat lost kind of equation. So those are looking at MC delta T, and are 2 ways that we're going to use those types of problems. And we're going to support this by doing a lab using just these calculations.